Okay, so far in this chapter, we've dealt with perpendicular bisectors. We've dealt with mid segments. And now we're going to be dealing with angle bisectors. And really, if you think about it, a mid-segment bisects a segment. It establishes a point in the middle called the midpoint. A perpendicular bisector bisects a segment. So in both of those two cases, you dealt with segments. Now we're moving to angles, still dealing with bisecting. An angle bisector is a ray that divides an angle into two congruent adjacent angles. It cuts the angle in half. Excuse me. Cuts it in half. So if I have an angle here that is 35 degrees, and then I have an angle bisector that cuts it into two equal halves, each one of these angles is 17.5 degrees. Not too tough. An angle bisector is a pretty easy thing to understand. Let's look at the theorems associated with it. The first theorem we come across is the angle bisector theorem. And what it says is that if a point, like point D, is on a bisector, then it is equidistant from the two sides. Meaning that since D is on the perpendicular bisector here, we can see it's the perpendicular bisector, we can see it's on the angle bisector because this angle and this angle are equal or congruent. If D is on the perpendicular or is on the angle bisector, then it is equidistant from the two sides, meaning BD and CD are the same length, which is why they wrote it right over here. Then we also see the converse, or the opposite of that, where if D is equidistant from the sides, then it's on the angle bisector. So up here we tell you an angle is being bisected, and so any point on that bisector is equidistant from the sides. Now we're saying a point is equidistant from the sides, therefore it's on the angle bisector. And that just falls under the converse. Okay? Here we're going from an angle bisected to equidistant from both sides. Here we're going from equidistant to the angle bisector. Okay? They're just backwards. That's all. Not a real hard concept to understand either. Maybe in this one they tell you that dB is 5 and that DC is 5. You can see first that D is equidistant. They're both 5. You can see they're perpendicular. Therefore, D is on the angle bisector, and that angle would be the same. Again, not too tough. Let's look at this example. A soccer goalie is standing in the middle of the goalpost, okay, standing directly between them, meaning that this side and this side are the same distance apart. If a striker takes a shot anyway, would it be harder to move to the left or to the right? Well, because the goalie is directly in between the two posts, he stands on the angle bisector. Whoops, I don't know why that did that. That's mean. He stands on the angle bisector, meaning the angle the striker is to the goal, okay, is cut in half. Half of that angle is over here. Half the angle is over here. And so it would be the same distance for him to go to his right or his left and his right, okay? Because he's in the middle, because both of these are the same distance, that striker or that, offensive guy, if he takes a shot, it's the same distance to either side. Not too tough. That's a real life example of an angle bisector anyway. Now let's actually look at some math behind it. If you have a problem here where we have an angle, we don't even need to know what angle it is. Maybe it's ABC. But we see right away that this angle and this angle are the same. That means that this point right here should be equidistant from both sides. That distance and that distance should be the same. Should be. If they're the same, we should be able to set them equal to each other. Well, if I divide both sides by 7 here, I get x equals 8. Meaning, if x equals 8, this side equals 56, and this side equals 56. Not too tough. We're told to find the value of x, which we did. Let's look over here. This problem is telling me that this point is equidistant from the sides. How do I know it's equidistant? They've given me congruency marks. And you were told in this theorem right here, the converse of the angle bisector, that if a point is equidistant from the endpoints, or equidistant from the sides of the angle, then it lies on the angle bisector. Because this point, we'll call it Harold. Because Harold is equidistant from the sides, then this should be an angle bisector, meaning this line right here should be an angle bisector. If it's an angle bisector, wouldn't these two angles be the same? Meaning, wouldn't 5x minus 4 and 4x plus 3 be equal? Well, if they were indeed equal, and if that is an angle bisector, we should be able to solve for x. So, let's use our algebra to solve this problem. The first thing I'm going to do is move all the x's to the same side. I'm going to move 4x to this side by subtraction. When I do that, they get canceled out. I drop down what I didn't use. 5x minus 4x is 1x minus 4 equals 3. And now I'm going to move this negative 4 to the other side because I want x by itself. When I do that, I get x equals 3 plus 4, which is 7. Not too tough. Let's talk about the concurrency of the angle bisectors. Last section we talked about the concurrency of the perpendicular bisectors. And we found out that if you have a triangle and you draw 3 perpendicular bisectors, okay, not too bad, then that point is equidistant from the 3 vertices. And that, actually, those 3 vertices or that point is also the center of a circle. Not too bad for freehand, right? Today what we're going to talk about is the concurrency of the angle bisectors. So let's take a triangle. And now we're going to be talking about the angle bisectors. And what you're going to see is that point, called the concurrency, has a characteristic very similar to the concurrency of the perpendicular bisectors. Let's take a look at it. The angle bisectors of a triangle intersect, which we can see right here. They intersect at point P. And that point is equidistant from the sides. This point, point P, is equidistant from the sides. Just like our perpendicular bisector is equidistant from the angles, our perpendicular bisector, I mean the angle bisectors. The angle bisectors are equidistant from the sides of the triangle. And let's keep our compass right here. If you'll notice, The perpendicular bisectors form the center of a circle. The angle bisectors form the center of a circle too. And in fact, that was a little bit off more. Sorry about that. I apologize. In fact, let's try that one more time. That's a little bit better. You'll notice that this circle is inside. I told you that this circle over here was called a what? Does anyone remember? This one was called a circumscribed circle. And the point inside of it was called the circumcenter. This type of circle, because it's inside the triangle, is called an inscribed circle. And this point, the center, is called the incenter. The incenter. We have a circumscribed circle with, come on, you can do it, with perpendicular bisectors. A circumscribed circle when you have perpendicular bisectors. And we have an inscribed circle when we have angle bisectors. Let's go back to our notes. That point is equidistant from the three sides. So that PD, PE, and PF are all the same length, right there. And we can use that information to solve for missing pieces, just like we did last section with the perpendicular bisectors. Just like perpendicular bisectors meet at a point of concurrency, so too do angle bisectors. Each angle bisector meets at a concurrent point that is equidistant from the three sides, just like this. The point of concurrency, which is right here, is also the center, called the incenter, of a circle drawn inside the circle. And we call that an inscribed circle. Your turn. One of the things that you're going to do tonight is you're going to be given a triangle, and you're going to see angle bisectors drawn. You're going to be shown that they're angle bisectors because the angles formed will be congruent to each other. And then you're going to be given some distances to the sides. Maybe this one is x, maybe this one is y, maybe this one is 8. Well, if all three of these distances are the same, then you could write x equals y equals 8, so that x equals 8 and y equals 8. You know, stuff like that. Or maybe maybe they have variables attached. Maybe it's going to be like 2x plus 4 equals 8, so that you've got to solve and get x to equal 2. You know, something like that. But those are the type of problems that you're going to have to solve tonight. You're going to have to know that these distances are congruent. They're the same. Set them equal to each other. And then use your algebra to solve those. Let's take a look at your homework now.